So a bit about my background. I started in biotechnology, fled from academia, entered a boot camp like I'm sure many of you all in the audience did. Bounced around the dev scene for a couple months here in the Bay Area, like I'm sure many of you in the audience currently are. And eventually I found my way into this big company, Bio-Rad, and I build natural language processing tools to help their scientists speed up research, do things more quickly, read papers without having to actually sit down and spend an hour reading all the new research papers. So it's a lot of search, relation extraction, trend analysis, things like that. So what I'm going to cover today, I'm going to cover two main overarching topics: word embeddings and clustering techniques. So essentially that's going to be how to represent natural language in a computer compatible format, and then how to sort through and meaningfully work with those computer compatible representations of natural language. Everybody following? Like, maybe just raise your hand if you've heard of word embeddings before, or word to vec, or natural language processing. All right, cool. All right. Oh dear, it's covering up my window. You guys are hugging me to death. Thank you. But if you guys want to look at the code demo here, I've got a GitHub link right here. So that's github.com/bendavidaaron/dumb-thesaurus. So give everybody a second to click that if they want to get through. All right, moving on. So like I was saying before, word embeddings are essentially a computer compatible way to represent language. Computers can't read, so we have to do something else. The first big breakthrough in this was called Bag of Words. That was initially published in 1954, where you take a document, you count all the words in it, and then you have a vector of all of your word counts. That's the length of your vocabulary. And congrats, it's machine readable. And this is a pretty coarse technique. It works pretty well for the amount of effort you generally have to put into it. And there's a few optimizations on top of it, like term frequency is kind of the beginning one, and then you can use term frequency inverse document frequency. So that's called TF-IDF right here. It's a little better at catching, unique terms within a document or unique terms within a corpus. Then in 2013, that's when word embeddings really turned into a big deal. But Word2Vec was published by Thomas Mikolov, who was working at Google at the time. And that's a neural network-based technique. So this really learns a lot more information about what a word is. Essentially, to train these, you build a bag of words. You then predict every individual word in your corpus based on a context window around that word. So you'll look at a sentence, Tom went to the store. And then the neural net will try to predict Tom from went to the store, and then went from Tom blank the store, and so on. And eventually you step through the whole of English Wikipedia, and you've now built a matrix of what words mean in high dimensional space. Am I following? Raise your hand if you're following. Anybody? All right, that's still a good number. And then essentially, once you finish training that network, then you just extract the hidden layers, and every slice, every row of that hidden layer matrix is going to be your actual word embeddings. So there's two trade-offs between these techniques. Bags of words, they're pretty coarse. They work for small applications, like your sentiment classifying tweets. Bag of words, yeah, you can do that just fine. Word embeddings are you're going to want those when you have a lot of money to get big compute resources because they're intense to train. The ones I work with in my day-to-day, the models usually take about 3 days to train running on an AWS C4 instance, which has like 16 cores, I think. It's a big computer. But you can learn a lot more cool stuff. You can learn a lot more detailed information about it that way. And there's other embedding types like fast text and BERT and Elmo, and they're all kind of just iterations on this Word2Vec technique. Fast text was actually developed by the initial author of Word2Vec. I'm going way too slow here. So then, clustering. Raise your hand if you've ever heard of clustering algorithms before, like nearest neighbors, k nearest neighbors. All right, good engagement. So what I'm going to talk about and what we're going to use today here is called approximate nearest neighbors, where instead of doing a pairwise calculation between every single data point in your corpus, which takes forever, you can draw random hyperplanes up to n times within your corpus to get a good enough clustering. and to get good enough nearest neighbors. So, like I was saying before, embeddings, they're good anywhere you have a big corpus to train with, document search, synonym finding, like we're about to do here, that sort of thing. If you can't represent it easily in software and the meaning of it is kind of arbitrary, that's where you want to use an embedding. And then nearest neighbors, anywhere you're clustering, exploratory data analysis, it's a big thing in active learning. If you have a data set and you have some intuition about what it means, but you don't have labels for it, clustering algorithms are always the spot you want to start at when you're trying to figure out, get to step one in a project. So now that I've kind of blown my time, let's go to the demo. We're going to do this real quick. So I'm going to fire up Jupyter here. And you can see I've got a couple wget commands. You can run all of this on your own time from the GitHub repository I've linked to in the slides. I've already pre-computed all of the indexes and everything. So actually, let's just stop that. Basically, you see, download it, unzip it. We glance at the file just to see what our word embeddings look like. In this case, we have comma, so that's a word. Period's a word. And we have the length of our vector file, just under 1 million, and the dimensionality of each vector. So 300 floating point values. Now we're going to wander down to where we're building our index. So we just load up the vectors, step through them, map it all out. If you guys want to go through this after the presentation, hit me up, slide my DMs on Slack. I'll be happy to talk through it slower in more detail. Let's see. We load up our neighborhood, and now we've got it ready to query. So somebody yell out a word. Oh man, I didn't realize the Zoom word.
Paper.
Deeper?
Paper.
Paper. Okay, let's get synonyms for paper. And we see paper, print, something out of our index, sheet, something else missing, area, design.
That's pretty cool.
Let's try something thematic, Python. Oh, well, Python's not in our data set. So this was trained using the 20 newsgroups data set. Obviously, that's a little limited. If we try something that'll obviously be in the news.
As long as Ruby isn't defined, but.
Yeah, if Ruby is in there. Nope,
Okay,
no Ruby.
Oh, that's good.
Good. So that's kind of the gist of it here. I know I packed a little too much information in there to be effective, but if anybody has questions, hit me up on Slack. I'll be floating around. I've got some links to word embeddings and nearest neighbors algorithms that I used in this presentation. If you'd like, you can go take a look, build your own thing, fork my repository, do whatever you want with it. And thanks for listening.